that'll suffice. Done. Share. I got it. Okay. Share my screen. Broadcast. All right. Who's going to make a group me, right? I think that's a good idea. Let me let the student in, Scott. Okay. Let me let these gentlemen in. I'm almost done with that first wave. So whoever comes after this is going to have to wait. I guess they got in. Okay. I think we kind of already. All right. So I'll check attendance again. Well, let me see. We still got a few seconds. Let me see. Okay. Yeah, literally a few seconds. Okay. So I'll check attendance again in about 15 minutes. That's just the way I do it. Because otherwise it's too disruptive. Let me go to view, single page. I don't like the way that looks. Come on. All right, that'll suffice. Okay. All right, welcome, scholars. Let's see. So we are officially starting week 2, right? I think last week we did our introduction. Hopefully you all are finding your way. You're able to gain access to the content. I know there was some confusion with some students as far as how to access it. They were looking for a code. There is no code, right? There's no course ID. The way you access the material, I think for this course, I linked everything into Blackboard. So for this calculus course, you have to access the content through Blackboard. And then you do have to purchase an access code, right? So there's no course ID. You access it through Blackboard and then you purchase full access to the site. Again, hopefully you all are making your way through the homework. If you've emailed me and I haven't responded, just ask me right now, like during class, like before we leave today. Or you can always, that's why I created an office cell phone number, right? Email is not the best way to communicate with me just because I get so many. And for whatever reason, students decide that they're going to that's the only way they're going to communicate. So I'm like, well, it just kind of lingers until I see it. Because when I'm not with you guys, I'm ripping and running the streets, like just trying to survive, right? So that's why I created an office cell phone number. That's going to be more effective, more efficient. You can text me at that number. You can text me anytime. And, and I'll respond much quicker because I know that that's you all. When I get emails, I get a ton of spam, a ton of emails that it's not necessarily spam, but, I don't need to, it doesn't pertain to me. And so it's easy for me to miss you all's emails, but it's still a good idea to email anyway, just to have it on file. But if you're really serious about getting your matter resolved timely, the best way to communicate with me is using the office cell phone number, right? Again, it's a dedicated line just for my students. So I know whenever I'm getting a call or a text to that line, I know it's you all, right? Otherwise, my emails is just a matter of getting my attention. So yeah, last week like I said, we did the intro and I think we did the first section. So again, for almost the first half of the semester, the rhythm is kind of intense. Now, fortunately, I want to say that we do have a recording. All the lectures are already recorded and available on my YouTube, right? So the link is available in Blackboard, and so that way you don't have to wait on me. Our goal for this week is to get through section 1.4, right? So idealistically, we can do 2 sections today, but it just depends. I don't really intend to rush because I have my recordings, and whatever we don't finish together, I do expect you to use my recordings. As we go through the presentation, if you have questions about anything, again, feel free to unmute yourself or type in the chat to get my attention. I am monitoring the chat, okay? All right, so let's see what we're working with today. So we're continuing chapter 1. I think chapter 1 has a total of 8 sections. Again, just the simplest way I could summarize differentiation, it's the slope of the tangent line at a point, all right? That is basically, we're talking about, it's like if we consider a curve and we consider a point on that curve, and we consider a line tangent to the curve at that point. And we're gonna dive deeper into all these terms that I'm using. But if I were to just summarize this as simply as I could, the best thing I could think to say is, again, differentiation is the slope of the tangent line at a point, right? And so now we're going to explore, well, how do we find that tangent line? Because you know how to find the slope. It's the same slope from college algebra and what you've been doing all the while. It's just the next progression, right? Okay. So I think last time we talked about limits, right? And limits, what we were concerned with was how does a function behave when we're really close to some x value, either on the left or the right, slightly to the left or slightly to the right of a given x value, right? Also with limits, sometimes we explore as x runs to positive infinity or as x runs to negative infinity. How does the function behave as x goes to positive infinity or negative infinity, right? So then here, we're going to be, and I'm so glad I do this before my other class, so my mind is more fresh and clear. Man, it's like, because this is my first class for the day. So here today, we're going to be looking at section 1.2, algebraic limits and continuity. Okay. So again, we kind of, last time we introduced the concept of a limit, so now we're going to see how to explore those limits algebraically. So a few objectives here. One, develop and use the limit properties to calculate limits. And two, determine whether a function is continuous at a point. Okay, not too bad. So we have some limit properties, slide 1 of 4. Okay, so let me do this. And again, I'll check attendance again just under 10 minutes, right at about 6:15 for the second wave of students. And it's crucial to get into that first wave. Because the most important things I say are like the first few minutes of class, to be honest. And I feel like that's generally any course. But again, these are recorded, so if you have to watch the recording, do what you got to do. So limit properties. The limit as x approaches a of f of x equals L, right? That's all it is. And the limit as x approaches a of g of x is M. And C is any constant, then we have the following properties. The first property is that L1, the limit of a constant is the constant, all right? So the limit as x approaches a of a constant is the constant, right? So what this is, like if we have some x and some y, right? And we consider some constant C, right? Then and no matter what x you choose, the y is always whatever that C. Right? Like for instance, if x were 2, y is just going to be C. If x were -7, y is always C. Right? So because it's a flat, constant function, as you approach any x value slightly to the left or the right, it's just going to be that number. Right? Hopefully that makes sense. So the limit as x approaches a of a constant is a constant. And again, if anything isn't clear, feel free to unmute yourself to get my attention and we can talk about it. The limit of a power function is the limit of the base raised to that power. So let me see. The limit of a power function is going to, basically, it's like you can pass the limit into the power, right? It's going to be the limit of the function raised to that power, right? Or the limit raised to that power. So the limit of a power is the power of the limit. That's the simplest way I can think to summarize that. Notice here for roots, right? It holds for roots as well. Mm-hmm. Assuming that our limit is non-negative, right? Where n is even. Okay, this is fine. That's just because, we can't take the even root of a negative number. Okay, and, also that I feel like it sinks in better, again, when you work examples. But the main takeaway here is when you're taking the limit of a power, it's almost like you can pass the limit into the power. Now we have the power of the limit, right? And it's the same thing for the second part. So then the third and fourth properties, the limit of a sum or a difference is the sum or difference of the limit. So we're starting with the limit of one function plus or minus another. By the end of it, it's just going to be the first limit plus or minus the second limit, right? And similar here for products, the limit of a product is going to be the product of the limits, right? Okay. So a few more properties. The limit of a quotient is the quotient of the limits, all right? So we have this quotient inside the limit, and then we can rewrite it as the quotient of the limits, as long as the bottom quotient is not 0. The limit of a constant times a function is going to be the constant times the limit. So it's almost like we can pull the constant out in front, right? Got about 6 minutes before I check the second wave. So if you have brothers like in the waiting room, just remind them. Yes.
Is it bad to be like confused right now? Because it's like low key, like when you're saying limit stuff, I'm not seeing numbers. So it's kind of like,
yeah, these are just properties, right? So this is like, these are some techniques that we're going to be able to apply. That's why I'm trying to get to an example because I do get what you're saying because it's like all it is just like like you're saying, it's
Yeah,
low
I keep
concrete.
hearing you say limit. I'm writing down everything you're saying, but I'm just trying
Mhm.
to get a
So
grasp.
I guess I would encourage you to like write down what you feel like you need to. Keep in mind that you do. I will make a copy of this available at the end of the presentation. I don't know what kind of device you're working on. It's probably better to like maybe screenshot this stuff if you're kind of as you go along.
Okay.
But again, you will get a copy of this. Um, and I really kind of intended to be a little bit more conversational. I just want you to kind of like listen, but write down whatever you feel like you need to. Um, but really just kind of like tune in as best you can. Um, again, this is just kind of introducing the properties. We're going to use these. I feel like once we start using the techniques, you'll see it a lot better, right? It's just a lot of properties. And then, I think this next slide showcases, right? Because this one is actually the power rule and the sum and difference rule in one go, right? So let's just see it in action. So this one says use the limit properties to find this limit, right? So with this, for instance, now if we use the sum and difference rule, we can rewrite this as the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 3x plus the limit as x approaches 4 of 7, right? So I just use the sum and difference rule limits, that property. I think it was like property 4 right here. I property 3. I just used property 3 just now, right? And it's kind of like distribute, right? So then for that first term, we just said the limit of a power is the same as the power of the limit, right? So we can rewrite that first term as the limit as x approaches 4 of x quantity squared, right? That's like the simplest form. We could rewrite that second one. So that second term we can write as the limit as x approaches 4 of 3. That's one limit. Then we're going to say times the limit as x approaches 4 of x, right? So that's like, so those are two separate. And then the last one, it says plus the limit as x approaches 4 is 7. The limit of a constant is just a constant, right? So that last one is really just plus 7. Okay, let's keep going. Let me move this. Okay. All right. So then if we keep going, the first one now, as x approaches 4, that limit is just it's just going to be 4, right? If you think about y equals x, it's just a diagonal line. As x approaches 4 coming from the left and the right, they both pretty much approach the y value of 4, right? So the limit as x approaches 4 is just going to be 4. So that's going to be 4 squared, right? The limit of a constant is itself, so that's going to be minus 3. X approaches 4 of x is just going to be 4 plus 7. So with something like this, essentially, really what we're doing is just plugging in, right? If you were to look at this quadratic, and then when x is 4, notice as if you let me see, let me pull up the graph. Let me pull up the graph. I'll do a rough sketch. We got a y-intercept. I'll pull it up right here. So let me see my calculator. Key. Is the calculator the best one? Reload and refresh. All right. So for instance, if we went to y equals and we type in x squared minus 3x plus 7, right? We can just do the standard graph. Y-intercept is 7. If we want to find that vertex, we can use the vertex formula, which is negative b over 2a. That'll give us our vertex. But we're concerned with as x approaches 4. So what I'm going to do, I'm going to go to trace. And I just want to see what's happening to the function, our y values, as we get closer and closer to x equals 4, right? So now x is 2, 2.5, 3, right? Notice the y values are getting closer. Let me see. Is it a clean number? Let me see. 16. Hang on. 16 minus 12 is 4 is 11, right? So as x gets closer and closer to 4, the y values are getting closer and closer to 11. And again, with something like this, I essentially just plugged it in, right? This one isn't too bad. So we got a limit of 11, right? Another way to kind of drive it home, here's our X, here's our Y. This is just a rough sketch. I'm going to say this is Y is 11, this is 4. Here's our 7. So we had some kind of image. I know it passes through like this point, something like this. Right? We have an image kind of like this, right? And so another way you can kind of conceptualize limits, if I do kind of like this, you can almost kind of envision like a vertical wall. Undo style. Kind of like a wall, right? Through x equals 4. Right? And we're concerning, okay, as x approaches 4 coming from the left, as we get closer and closer to 4 coming this way, what's happening to our y value? Y is getting closer and closer to this 11 here. Right? Y is getting closer and closer. As we approach 4 coming from the right, notice the y values are still getting closer and closer to that 11. Right? So that's essentially what we're talking about here. Right? Let's try this. So as we get this way, no, forget it. Let's just go with that. Okay, but I feel like this is a little bit oversimplification. In this example, essentially what we did is we just plugged in 4. Now we're going to see examples where you can't just plug in and it doesn't work. So we're going to try some other techniques. But at first glance, you can try just plugging in and see if that works. Right. So we got 11 here. Okay, let's just go with that for now. And let's just try let's try two more examples and then see if we can get it to sync in by then. Okay, style. Okay, let's try another. Oh, what's the time? Let me get these gentlemen. So I need this. That looks good. Let's go here. Let me adjust this. Come on. Let's see. That's 7. That looks good. Oh yeah, we got a good amount. Okay. All right. This one. This one. This one. This one. Let me stop this. I mean, I know it's kind of late now, but housing. Did I get him? Got him. This one. Okay. That name definitely looks familiar. HIG. Here he is. So, man, we got a good amount. I feel like I went fishing or something. I don't know who that is. I'm gonna have to let them know, hey, you gotta show your student name to get credit. Davis. Okay. I'm gonna let that load for a hot second. Let me check the chat. Okay, so let me share my screen real quick. There was one user I just added. It just says Zoom user, so I wasn't able to update my attendance with your name because I don't know who you are. So just you can DM me here, DM me, like send me a direct message so I can and update your username so that it shows your student name, so I can be sure that going forward I can give you attendance credit. You can get it today. I need you to identify yourself. No. Only the one that said Zoom user, not everybody. Right? I got everybody else. Just the person that says Zoom user. Yeah, I got everybody else. Let me see. Ooh, thought I made a mistake.
Are you doing attendance right now?
I do it automatically. I do it as I let you guys in. So I've already done it for everybody else. Give me a second. I saw the name I needed to see. I'm just trying to update my attendance. Let's see. Hang on. Right here. Here it is. This one. And this one, okay. Yeah, the way so that's how I like the way I do my attendance. Yeah, I think I got everybody. Yeah. Okay. So the way I do my attendance is I let you go. I manually let you all into the waiting room. So I have you wait in the waiting room. So then when I go to check it, when I go to let you in, I take attendance as I let you in, right? So that's why I do waves. I do one wave about 5 minutes before the start of class. I get everybody so that way we can start on time. But again, I let each student in one by one, and I'm taking names as I do it. And then I did the same thing just now with the 15-minute, the second one. It was just one person; their name wasn't showing, so I didn't know who they were. But he emailed me, so I was able to update it. Yeah, if you're just joining us, you have to use the recording to get the intro for today, and make sure you have that information. And you can find it on my YouTube channel because I'm doing this. I am live streaming these sessions directly to my YouTube, so you can always reference that at your leisure. Okay, so we got 11 for this one, and again, the oversimplification here is I essentially did just plug in the 4, but I tried to like break it apart so you can see the applications of those properties we just introduced. Right? Okay, let's try another one. Let me see. 16. Let's see. 11. There's the result there. Now, this looks a lot cleaner than what I'm doing. I really like how that looks. Hey, thanks. Thank you. That's enough. Which we have in class. Like she's been quiet all day and now she want to start screaming. Thank you. Thank you. All right. So for any rational function f with a in the domain of f, the limit as x approaches ac. So this is essentially what I just did in the previous, right? The limit as x approaches a of f of x is really just going to be f of a. So that's what I did in the previous. Says for any rational function f with a in the domain of f, so as long as a is in the domain of your rational function, then you can just plug it in, right? That's essentially what I did. Okay, so find the limit as x approaches 0 of this guy. So now we could apply the power rule, right? Where we can pass this limit through the radical. Sure, I guess we can do that. I mean, it said rational functions, but I think here we can just try plugging in as well. All right. So let's see. If I were to just plug it in, if we just here, let's apply the power rule first, right? So if we apply the power rule, we can rewrite this guy as the square root of the limit as x approaches 0 of x squared minus the limit as x approaches 0 of 3x plus the limit as x approaches 0 of 2. And we can just pass it. We can pass it through the radical like this, right? There are a few other stipulations, but I think we're okay for now. So now, at this point, we have like 3 separate rational functions, right? Like here's a rational function, here's a second and a third. So then with those, we can just plug in, right? That's why I broke it apart. So then this is going to be the square root of 0 squared minus 3 times 0 plus 2. Looks like it's just the square root of 2. Now let's just do this. All right. So because I started to just plug it in off the rip, but I was like, okay, well, let's actually apply what we just introduced in the previous slide. So then I was like, in order to apply it, that only applied to rational functions. So I applied one of those properties for limits first, and then I applied the previous slide. Again, forget all of that. The simple thing right now is we can just plug in. Now, again, we don't always have that luxury of just plugging in, but whenever we can, we do. All right, or we just try that first. Okay, so we got square root of 2 here. And again, like if you were, another way you can check this, like if you wanted to look at a table, you can make a table of values, right? You can have your x versus your f of x. And then like say you were considering this like as x approaches 0 from the left side, right? So choosing numbers left of 0, you might choose numbers like negative 0.2, negative 0.1, negative 0.01, 0.001, right? So you can choose and just keep adding zeros between the decimal and the 1. And the longer the more zeros you add, the better approximation you're going to get. And so that'll give you a sense of the limit coming from the left. And then if you wanted to see it from the right, as x approaches 0 from the right of this function, you can do, basically it's the same thing, just remove the negative. So you can do like 0.2, and then do 0.1, and then do 0.01, and then do 0.001, right? And just kind of keep going, keep adding zeros. And in either case, the more zeros you add, those numbers should get closer and closer and closer to the square root of 2, right? So as we approach 0 coming from the left and from the right, the y values are both approaching this number that we have in the box, okay? Okay, let's try another one. So hopefully that should be a little bit more clear than the first one, right? So now let's see if we can get another one, right? Again, we just get the square root of 2. The theorem on limits of rational functions and limit property 2, that's exactly what we did.
Excuse me.
Yes.
So if we have like one of these questions on the homework, say we do, will we just need to find the answer, or do we have to make the table too?
Just the answer. I mean, the prompts, just follow the prompts, right? Because a lot of times they just want the answer. Sometimes they do want you to kind of fill in the steps, but they give clear instructions. All right. So yeah, just if you just kind of like follow the prompts, like if you already have the answer in mind and you understand like enough of the concept behind it, then you can just answer whatever question. A lot of times it's just they just want the answer.
So you're saying the table just helps you a little bit more?
Yeah, with the concepts, because sometimes you can't just plug in and just get the answer, right? Like sometimes you can't just plug in and just produce a number like square root of 2. So if that doesn't work, you might try a table. All right, you might try, okay, if we're considering when x is 3, but we can't just plug in, well, let's see what happens when we're close to 3 coming from the left. Let's see what happens when we're close to 3 coming from the right, right? And we're going to explore some other techniques as well, right? But a table is an alternate method than just plugging in. All right, we have some more techniques coming down the pipeline too. Yeah, these are good questions. I like this kind of stuff. All right, okay, let's see. So we saw 2 examples. I'm going to leave the quick check as practice or exercise for you. You got the results there. It's a good amount. Come on. Okay, let's give this one a go. I'm gonna have to fix that later. Find the limit as x approaches -3 of this guy. Now notice with this one, if we try to plug in -3, something happens. All right, what happens? If we plug in, and I'll do this one, I'll do it in purple, I guess. So if we try to just plug in when x is -3, notice the following. All right, you should hopefully you see it by now. Right? I think we get what, 0 over 0, and that's like no good. All right, we can't use that. So now with this one, I want to say we can actually simplify. Right? Let me put it next to this. Right? We can't use this, but I want to leave that just to showcase we can't just plug in. But I think with this one we can simplify it down first. Now I think we should make a note that x cannot be equal to -3. But if we were to simplify, like if we start with the limit as x, and now, or you could do the table. You could do a table slightly to the left of -3 and slightly to the right. They should approach, if the limit exists, they should approach the same number. But let me try this other technique. So as x approaches -3, now we were given x squared minus 9 over x plus 3, right? Let's simplify this down. That numerator looks like we can factor it, right? It's difference of squares, so it factors. Let me see, the limit as x approaches 3, it's going to be x minus 3 times x plus 3 over x plus 3, right? So then what do you notice? This cancels this, right? So then that leaves us with the limit as x approaches 3 of x minus 3, right? So I want to say with this one, we can just plug in, all right? So we get a value of 6. So what this is saying, like if we were to look at this graph and, wait a minute. Wait. I dropped off my negative. Hang tight. It looks like we had -6. I think I dropped off my negative. Like a negative there, a negative there. So we get -6 as a result. Can I just paste? Okay. Okay, that should be the result. Copy. All right. Again, one way we could check, we can make a table, right? Numbers slightly to the left of -3 will be like negative 3.1, negative 3.01, negative 3.001, right? And you should get numbers to get closer and closer to negative 6. Numbers slightly to the right of negative 3 would be negative 2.9, negative 2.99, negative 2.999, 2 point quad 9, yada, yada, yada. Those should get closer and closer to negative 6, right? But again, the main takeaway here, we tried to plug in originally. We got 0 over 0, so we had to go back and try something else. We could have done the table, but what we ended up doing was we simplified the rational expression. We got it down to a linear function, and then we just plugged in, and we got negative 6. Let's see if that's correct. Okay. So note that does not immediately apply because negative 3 is not in the domain of this rational function. However, if we simplify first, the result can be evaluated when x is negative 3, and we get negative 6. Right? I think they did the exact same thing that we did. So this means that the limit exists as x approaches negative 3, but the actual point from the previous slide does not exist. But it does not, right? So again, the takeaway with limits is we're not really concerned with what happens at the point, because this function is not defined when x is negative 3, but the limit is concerned with what happens when we're close, slightly to the left or slightly to the right, right? Slightly to the left of negative 3 or slightly to the right of negative 3, the corresponding y's are getting closer and closer to negative 6. But if you're right on the money when x is negative 3, the function is not defined, right? So again, limit is concerned with when we're close to a number, not the actual number itself, right? So this whole discussion, like with limits, is kind of like bringing up this notion in mathematics that's like unique to mathematics. This whole thing about precision, like when you're being exact. Like a lot of concepts in mathematics are concerned with, okay, what happens when you're on the money and what happens when you're close, like, and then what happens when you're as far away as possible, right? Those seem to be the main dynamics: on the money, when you're close, or when you're really far away, right? And it took a while for that to sink in for me, but here we're really concerned with what's happening when we're close to the target. And the funny thing is, I actually use this in my gaming a lot. Like not consciously, I'm not like sitting and doing calculations, but like when I'm doing like the multiplayer games, and if I choose anybody with any kind of long range anything, I'm like, okay, like some of them are snipers. You have to you can't shoot where they are. You got to shoot where they're going to be, right? And so it's like, okay, and there's this little like guide that pops up. Like if I do it right, if I target them directly and they move, then I miss. And sometimes it has like little hairs on the side, and sometimes I'll use those hairs because I know they're going this direction, and I'll use that as a guide to like shoot where they're going to be, and then they'll collide with my bullet, right? So it's really interesting. And sometimes it's like way off, and I just throw a Hail Mary, and it'll get them. But yeah. So again, the concepts here are that we're kind of discussing. One concept is when you're exactly on that number, what happens, right? And that's kind of like traditional math that you're used to doing, like in pre-calculus and college algebra and stuff like that. Something that's new here is we're exploring what happens when we're close to these numbers, right? And then, in the extreme cases, as far as like x on a positive infinity or negative infinity, that's another one as well. Okay. All right. So let's give this one a go. Oh, okay. So here's a case where the limit is x tends to infinity. So now with something like this, there is a technique that I would recommend that you do first, right? We're going to factor out 1 in a certain form so that we can take the limit as x tends to infinity, right? So we notice that we have like 6 terms, 3 terms on top, 3 terms on bottom. If we focus on each term, the highest power is that power of 2. So I'm going to factor out x squared from all the terms. I'm going to factor out 1 in the form of x squared over x squared, and then try to evaluate this. Because if we try to plug in infinity now, we're going to have infinity squared, and which goes to infinity, right? So it's just, we can't process that, right? So let's try this technique of rewriting or factoring out 1, right? So then we can rewrite this guy as the limit as x tends to infinity. Now we're factoring out 1 in the form of x squared over x squared, right? Okay. So then now if we factor out x squared over x squared, from the numerator, the first term becomes 1, plus the second term is going to become 4 over x, minus the third term is going to become 5 over x squared. Okay, what's the time? And then the first term in the denominator is just going to be a 2, right? Plus 1 over x plus 1 over x squared. Okay? So now something divided by itself, this expression goes to 1, right? So it just kind of, they cancel each other out. So now we're considering the limit as x, clean that up. The limit as x tends to infinity. Now we have 1 plus 4 over x minus 5 over x squared over 2 plus 1 over x plus 1 over x squared, right? So now essentially just kind of plug in the concept of infinity, right? So what do we mean by this? For instance, let's focus on this guy here. Let's change this color, right? Now we want to consider this as x tends to infinity, right? Well, what happens when x is 1? If x is 1, we get 1. When x is 2, well, we get a half. When x is 4, we get a quarter, and then an eighth, and then a 16th, and then a 32nd, and then a 64. So what do you notice as x is getting bigger and bigger and bigger? What's happening to this fraction? Because we have a fixed numerator, and this denominator is getting bigger and bigger and bigger, what's happening to this overall term?
It's getting smaller.
This fraction is time, right? We want to consider what happens to this guy specifically as x gets bigger and bigger and bigger and bigger, right? As x tends to infinity. So let's start with something we know. We know, well, when x is 1, 1 divided by 1 is 1. Well, when x is 2, 1 divided by 2 is a half. When x is 4, it's a quarter, and then an eighth, and then a 16th, and then a 32nd, and then a 6th and bigger. This fraction is getting smaller and smaller and smaller. You can see it by now. So as x tends to 0, same for this guy tends to 0. All of these guys, because they have fixed numerators, they all tend to 0, right? So as we pass the limit, and the limit of a constant is itself, so now what we're saying is as x goes off to positive infinity, our expression transforms into 1 plus 0
Wait,
minus.
excuse me.
I'm just, write it down. I'm just about done with this one, and then we can answer. Yeah, we're just about done, right? So then our claim is that as x tends to infinity, the function, our y value gets closer and closer and closer to 1/2, right? Okay, go ahead.
I was saying, why did you zero them up?
So okay. Let's go back to this guy, right? If we just focus on the red circle, just that one term by itself, we're concerned with what happens as x gets really, really large, right? Tell me, when x is 1, what's 1 divided by 1?
1.
Are you still there?
1. You said 1 divided by 1. 1.
Well, once. Yeah. So So 1 divided by 1 is 1. So again, we're concerned with what happens as x gets really large. So when x is 2, what's that result?
I can't really hear you, Dr. Pfeiffer. You're going in and out.
All right, sorry about that. Let's try that again. Let me share my screen. Start the broadcast. All right, optimize. I'm not sure how much of that presentation you all heard. Let me just do it one more time because for whatever reason the connection got lost. You guys can hear me okay? Let's see. Testing, testing. I think it's okay. All right. So, with this term, with each of these terms, again, what we're concerned with, what happens is the denominator gets really big, right? So, for instance, we start with numbers that we know. When x is 1, then 1 divided by when x is 4, that's a quarter, then a 32nd, and then a 64, and a 1024, right? As this term, this expression gets closer and fixed, those denominators as they get, oh my goodness. Yeah, I don't know why it keeps knocking us off. Let me see. Yeah, I don't know what to do about that. Are you guys there? Can you hear me?
Yeah.
You're
Yes.
breaking up though.
Yes, you're breaking up.
Yeah, you breaking up real bad. Like when you explain, you like going skips.
Yeah, all I can do is try again. Like, I don't know. But this because of stuff like this is why I have my pre-recorded lectures, because there's nothing like, everything is off, I don't know. But we do the best we can with whatever time we have together. But this is why I made pre-recorded lectures. So whatever we don't finish together, I do expect you to use my pre-recorded lectures to watch at your leisure, take notes, write down your questions, and email me. But the best is still use my office cell phone number. Honestly, you can text me at that number at any time. I haven't had any issues with it, and like I've been going back and forth with students sometimes in the middle of the night. That's usually when I'm up. It's like 3, 4 in the morning. And then I go to sleep when the sun comes up. But let me try this one more time. I do know that, I don't know, for whatever reason it keeps booting off. But again, whatever we don't do together, I do expect you to use my recorded lectures. Anything that I'm saying here live is already in those recordings. So if we focus on this term, right, we're concerned with what happens as the denominator gets really large. So if we start with the denominator that we know and keep growing, we can get a sense, right? So for instance, when this denominator is a 1, 1 divided by 1 is 1. When that denominator is 2, 1 divided by 2 is a half. And then a quarter, and then an eighth, and then a 16th, a 32nd, right? So as those denominators get bigger and bigger and bigger, this term gets closer and closer and closer to 0. So as x tends to infinity, this whole thing tends to 0. And then once you understand for one of these terms, it's the exact same concept for the other 3, right? So once you get one, then the other 3 are the same concept. So then those lead to this, right? And that leads to this, right? That's about the best we could do. I don't know. The network, that's what it does sometimes. It's out of our control. But again, my response for those kind of issues, and it's eating up our time, that's why I made those pre-recorded lectures, right? So we're not so heavily dependent on this live session. This is just something added or extra. Okay, so we're gonna have to kind of let that be for right now. Let's try another one. I'm gonna leave that as an exercise. Let's look at this definition. So we say a function f is continuous at x equals a if, okay, so continuous at a point, right? So we say what? F of a exists, the output at a exists. The limit as x approaches f of a exists. So this is the limit as x approaches a. And the limit as x approaches a of f of x equals f of a. The limit is the same as the output, right? So this is our definition for saying that a function is continuous at a given point. The function has to exist at that value of a. the limit as x approaches a of f of x has to exist. And the third part is basically part one has to equal part two. Let me say that one more time. So we have three conditions to say that a function is continuous at a point x equals a. First, the function has to exist at that value of a. Second, the limit as x approaches a of f of a exists, right? So the limit exists. So the left-hand limit equals the right-hand limit kind of stuff. And then three, part one has to equal part two. So the limit as x approaches a of f of x equals f of a. So then when all three of those conditions are satisfied, then we say a function is continuous at that point x equals a. Now we say that a function is continuous over an interval from C to D if it is continuous at each point in that interval, right? So once you can define a function being continuous at a point, then you can extend that to an open interval between two other points, right? And we say that the function is continuous over the interval as long as that function is continuous at each point in that interval, right? Okay, let me see the time. We have a solid 30 minutes, give or take. Let's just keep going. Let me see. So if this function given by this is continuous at equals, or is this function given continuous when x is 3? Okay, so in order for it to be continuous when x is 3, we have to show that it satisfies those three conditions, right? So the first one is we need to show that what f of 3 exists. So if we do f of 3, that's going to be what, 4, right? So that condition is satisfied, right? It's defined when x is 3. Okay. Second, we need to show that what the limit as x approaches 3 of this function exists. Okay. So then 2, the limit as x approaches 3 of, now we got this x squared minus 5. Now we can apply those limit properties that we introduced, right? We can, or you can just plug it in, right? We can rewrite this as the limit as x approaches 3 of x squared minus the limit as x approaches 3 of 5. Okay, that's going to be 9 minus 5, which is 4, right? So that one checks out. And I feel like this kind of dialogue will be a little bit more clear when we come to an example that's not continuous at a point, right? We'll see that in just a moment. So then the third part is part 1 needs to equal part 2, and they do, right? The limit as x approaches 3 of x squared minus 5 equals f of 3, right? So then, because they're already equal, all right? So because conditions 1, 2, and 3 are satisfied, then we can say that the function is continuous at x equals 3. Okay. Let me see if I can find an example where it's not continuous. Okay. Okay, so is this function given by here continuous when x is -2? Okay, so let's try verifying those same conditions with this example. So first, again, we need to show what g of -2, does it exist? So if we're working -2, it looks like we use what, line 2, because that's when x is equal to -2. So then that means we're going to have -2 minus 1, which is -3. So it does exist, right? So the function is defined when x is -2, okay? Now, we need to explore the limit as x approaches -2. So because this is a piecewise function, and it seems like, something happens on either side of -2, we might need to break the limit up into parts, right? So first, let's evaluate the limit as x approaches -2. Let's evaluate it as it approaches coming from the left. Okay. Now, as we approach -2 from the left, you gotta be clear. Do we use line 1 or do we use line 2? Well, if we're approaching x from the -2 from the left, we're going to use line 1, right? So then the limit as x approaches -2 of this 1/2 x plus 3. Okay. So that's going to be -1. Nope. -1 plus 3, which is 2. So the limit as x approaches -2 from the left is going to be 2. Let's evaluate the limit as x approaches -2 from the right. Now, as we approach -2 from the right, we're going to use line 2. So we're going to have this x minus 1. So now when we plug in -2, it's going to be -2 minus 1, which is -3, right? So notice that the limit from the left does not equal the limit from the right. And that's the very condition that we have that says the limit does not exist. Because the left-hand limit does not equal the right-hand limit, then we say that the limit does not exist. So 2 fails, so it's not continuous at that point. So we'll say the limit does not exist. The limit as x approaches -2 of f of x or g of x, g of x does not exist because the left-hand limit does not equal the right-hand limit, right? So then because that one fails, it's not continuous at x equals -2. Okay. All right. So 2 fails. Right here. Just about out of time. So again, yeah, this is exactly what we did. So since the limit as x approaches -2 from the left of g of x does not equal the limit as x approaches -2 from the right, then the limit as x approaches -2 does not exist. Therefore, g is not continuous, right? Again, I'm reading all of this. The left is identified by this guy. The right is identified by this guy. Because the left doesn't equal the right, then we say that this limit does not exist. So therefore, g is not continuous at x equals -2. Okay. We just about got through this section. Quick check, I'll leave as an exercise. Oh, okay, I think we did. We got through this one. I'll leave that for you. We don't really have enough time to get to the next section. Yeah, I think I'm just gonna stop here. I know we have another 15 minutes. I do have another class I need to I do have a time conflict. Are there any burning questions? I feel like there should be questions. You just have to do the best that you can. I think a group me is a good idea. I think collaborating with the tutor is a good idea. Making use of my office hours. Again, I can't stress it enough. Emailing me is fine, but if you really want like a prompt response, the best is either call my office cell phone or just text my office cell phone, right? You can send text messages there as well. And then we can kind of go back and forth and resolve the matter. Email, that's not the best way to communicate with me because I don't notice it until like a week later or so. I just don't notice it. Okay, if there aren't any other burning questions, then we're just going to go ahead and end the session.
I have a question.
Yes.
So would you say we should go ahead and start like as we're learning through the lessons, like as we go through certain sections, like do the homework as is, or we could go ahead and just go ahead and what I'm saying, if we're understanding a topic.
Yeah. Like if you feel confident in it, yeah, you can definitely just go ahead and start on the homework. Like, yeah, you do want to try to get through this stuff as quickly as possible. You obviously each person's going to have their own rhythm or rate, and then if something's clear, that's when you kind of like, okay, wait, let me go back and look at that recording, or let me, you have to dig a little deeper. But yeah, you definitely want to try to get out as far ahead as you can. And honestly, all the assignments are posted with the exception of the exams. The recordings for each section is already available. Like anything that I would say live is already in those pre-recordings, so you really don't have to wait on me. And then if anything isn't clear, like if you get stuck or have a question, email me. But again, the best response, send me a text to my office cell phone number, right? So that you can keep moving.
I got a question. So when are the assignments due?
The due dates are next to each assignment in Pearson. Like for instance, if I log into Pearson, this one, Allow. Sign in. Come on. This is calculus. Allow. This one. Let's see. Calculus. I think this is the proper one, right? When you log in, it says due on the left-hand side. So like these assignments are due, I think like a week from today, the 29th. The first few assignments, I think I made them do, I give you like the first 2 weeks for the first few assignments because I know people are still getting access and stuff. Sorry, stuff like that. So first few assignments are due pretty much at the end of week 2 or the start of week 3. All right, but the due dates are to the left on the left-hand panel. Okay, any other burning questions?
Yeah, I have one quick question.
Yes.
I was here, but I didn't hear when you said how do we get our MyLab login? Is it just our email?
So to access my math lab, let me show you that one. So from there, we do that from Blackboard. So if I go to like my Morehouse portal, and if I log into Blackboard, let me see. Okay. Come on. This is taking a sweet time. Log in. Okay. So where's Blackboard? Here it is. So if I go to Blackboard and log into our course, on the left-hand side, it says courses. And then for us, is calculus for business. And so to access the homework, this should be the landing page. It should look like this. And it says calculus for business spring 24. We open up that folder. And then item number 3, it says all assignments. So we click on that. And then the first link, it says My Lab and Mastering All Assignments. We click there. And okay, well, yours is going to look a little different because it's going to prompt you to register as a student. After you register, you do have to purchase full access, right? But after you register and everything, it's going to look like this, right? And this is where you access it. But you access it through Blackboard. And you have to pay for an access code. And it costs like just under $130. Something like that. At least that's my understanding. Okay. Any other burning questions going once, going twice? Okay. So yeah, hopefully you all have like made a plan and you're taking action. If there aren't any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. We'll meet back on Wednesday, same time, same place. All right, guys, take care. Peace. Let me check the chat real quick. Okay. Yeah. So